Okay, let's start. Quick announcement, homework is due today. We've moved the deadline for the due date for the homeworks to Thursday from now on. I guess that works better with office hours for most of you. The impression I've gotten from you guys coming to office hours is that the homework is taking a long time, more than 10 hours. So we'll try to, I'll try to give feedback to Al to make the problems easier on you guys. You can blame him for all the hard problems. No, I'm kidding. Okay, so let's kind of recap where we were last lecture. So we started looking at nonlinear circuits and distortion. Now, even though I didn't say it, and this is lecture 8, even though I didn't say it, what we're looking at up to now is what we call weak nonlinearity. So I want to emphasize that we're studying weak nonlinearity. Or, if you like, small signal distortion. So the idea is that we're driving the amplifiers with relatively small signals, and we're looking at the distortion products, which up to now for linear circuits we completely ignored, but now we see that there's going to be some small amount of distortion. When there's gross amount of distortion, the analysis, the power series analysis that we do actually doesn't apply. So what this power series analysis lets us do is predict at least when the distortion is going to be so gross that it's going to require more sophisticated analysis. So we're still, if we take a simple amplifier and we bias it someplace, let's say VBEQ, we're still putting a relatively small signal on here, and then at the collector we get our output signal, and on top of it we're going to get this harmonic distortion. But the harmonic distortion is a relatively small part. So let's say it's a factor of at least 10 smaller than the main signal. Okay. Now if we look at, let's say, the typical curve, let's say a nonlinear curve for a device, and we consider applying a small signal, then we can see that doing a Taylor series expansion around this point in this region is going to be quite accurate. It's going to, even just a simple third order polynomial will describe pretty accurately the shape of this curve. As the signal becomes larger and larger, we know we have to make our Taylor series expansion longer and longer to retain the accuracy. Remember, the remainder theorem in the Taylor series approximation tells us roughly what the remainder is after the difference between the real function and the Taylor series expansion. So what we'd like to do is not carry around, 60 terms in the polynomial. We want to deal with maybe 2, maybe 3 or 4. For the most part, we'll deal with third order polynomials. So that means that we use third order polynomial to understand the system. As you'll see in this class, if we had to carry around more terms, it would become very, very painful. Even 3 terms gets pretty messy, as we'll see. So the goal is to study what's the right word I'm looking for? Basically, we're still studying small signal circuits, but we're just expanding our viewpoint to understand how small signal circuits generate distortion. Now, so last lecture we modeled our system that the output signal is going to be some linear function of the input plus some polynomial function of the input plus some cubic function of the input, and so on and so forth. And we use a binomial expansion to look at the general nth term products generated when we put a sinusoidal in. Now, if you like math, that's a good way to do it. Let's look at it a slightly different way today, which is maybe simpler. So let's say our input, let's just consider a simple cosine at some frequency, cosine omega 1. If I multiply this by cosine omega 2, I can use my trigonometric identity that cosine A plus B is equal to cosine A cosine B minus sine A sine B. That's from trigonometry. I can take this expression, plug in cosine A minus B. That's also cosine A cosine B because cosine is an even function. But now, because sine is an odd function, I get plus sine A sine B. Now, if I take the sum of these two terms, what I get is cosine A plus B plus cosine A minus B is equal to, we can see this term cancels out, and on the right-hand side we just get two of these terms, cosine A cosine B. So this is actually a very useful identity. If you can memorize it, if you can't, learn to derive it. Basically all the results that we've derived so far can be basically obtained from this solution. So let's see how this applies. So let's take something like cosine squared. Well, cosine squared looks like cosine A times cosine A, so that's equal to 1/2 cosine omega 1 plus omega 1t, right? That's that term, plus cosine omega 1 minus omega 1t, and that's that term. And so this, of course, is just 1, so we get 1/2 1, and this is cosine 2 omega 1t. Of course, most of you knew this result by heart, but you can see that you could derive it from here. Now, because we do a polynomial expansion, essentially all we're doing is multiplying cosines together. So we can keep using this trigonometric identity to our benefit. So, for instance, look at cosine cubed. So if I want to take cosine cubed, I can just multiply this expression by cosine omega 1t, and the first term just gives me 1/2 cosine omega 1t, and then I have 1/2 cosine omega 1t cosine 2 omega 1t. And again, I'm going to apply this identity and expand this product. So now I have 1/2 cosine omega 1t plus 1/2, basically 1/2 times 1/2, sum frequency and difference frequency. So the important point to take away is when you multiply two cosines, you get a sum cosine and you get a difference cosine, right? And basically it looks like one cosine is modulating the other cosine. So the sum frequency and you get a difference frequency. So the sum frequency here is cosine 3 omega 1t, and the difference frequency is cosine omega 1t. So we see that the cubic generated fundamental and third harmonic. That, of course, matches the results we did last time when we did the binomial expansion. If I sum here, I get 1/4 plus 1/2, or 3/4 cosine omega 1t plus 1/4 cosine 3 omega 1t. Okay? And so we see that cubic will generate fundamental and it will generate third harmonic. And last lecture, what we proved was more generally that any even power will generate even harmonics, right, including DC, and any odd power will generate all odd harmonics, including starting from the fundamental. Okay, so that's a quick recap from last lecture. If we now take into account that no matter how complicated, how many terms we have in the polynomial, essentially the output, so we have a system where we plug in, let's say, cosine omega 1t with some amplitude. So this is a nonlinear system. It's memoryless. And the output basically is going to be a sum vi cosine, I'll call this n, cosine n omega 1t, where n goes from 0 to infinity. We call this a weak nonlinearity. Again, that's the assumption that we're not putting too big of a signal into our system. And we'll quantify that statement later on when we look at some practical examples. But no matter, basically, so what we've seen is no matter what's inside this black box, we can represent it as some nonlinear function, right, f of v in, and we do a Taylor series expansion on f of v in, and for a sinusoidal input, it just generates harmonics of the output. So the fundamental v1 cosine omega 1t is the desired tone. Everything else is distortion. Okay. Any questions? Yes.
Last lecture, you had drawn a curve in which you showed that as we go on, like how the third harmonic and second harmonic catch up.
I'm going to draw that curve again.
Okay, is that also small signal?
We'll talk about that. Yeah, so hold that thought. Okay. Any other questions or comments up to here? So the framework should be hopefully clear by now. And so now we're going to, if you understand up to here, the rest of the lecture is just a bunch of definitions. So take your time and ask some questions. Vincent?
Yeah, for this starting here, what would be a strong nonlinear system look like? I thought any output can be expanded with Taylor series and harmonics.
Okay. Very ugly, that's the answer. What would it look like? It'd be very ugly. No, seriously, if you study power series expansion, you know there's a radius of convergence, right? And basically, if you want a certain error in the Taylor series expansion, then the radius will become smaller and smaller. So not every function has a Taylor series expansion to begin with. And furthermore, to get the desired error may require to carry 20 terms in your Taylor series expansion. Now, a computer can do that no problem. I have trouble doing 3 terms actually, so doing even 5 would be very painful to me. Okay? Any other questions? Okay, so let's draw that picture from last lecture. I have to be careful how I draw this picture, otherwise it turns out funny. Let me assume that I have a log scale, and this is my input amplitude. So let me start out at 1 microvolt, 10 micro, 100 micro, millivolt, 10 millivolts. And here, likewise, 1 micro, 10 micro, 100 micro, 1 milli, 10 milli, 100 milli, and so on. So let me assume that I have a gain of 100. So that means if I have an input at 1 microvolt, my output will be 100 microvolts. Okay? And so on. So if I put in 10 microvolts, I should have 1 millivolt output. So this is a curve of the output voltage versus the input voltage, right, on a log scale. And the reason I'm drawing dashed lines here is I don't know what's happening when I put in really large signals, but if I put in very small signals like a microvolt, I know that essentially the system is going to act more or less linearly, and this line should be pretty flat. Okay? Now, let's draw the same curve for second order. Let's say that when I put in 1 microvolt, the output from the second order is also 1 microvolt. Let me put it here. Okay. So that means that, well, that's actually not so good. Let me put it here. Let's say it's 100 nanovolts. Forget that point. So what happens if I increase the input amplitude by a factor of 10? What happens to the second order distortion product? Exactly. It goes up by a factor of 100 because, remember, the second order is proportional to Vn squared. So here is the second point. So this is the curve. So this is the fundamental. This is Vi2, or let's just say V2, the output second harmonic. Likewise, if I look at the third, let me expand this curve here. This is 10 nano. Let's say my third is here. If I increase the input by a factor of 10, what happens to the third? Well, I think you get the point. It's cubed, so it should increase by a factor of 1,000. So my third harmonic has a slope that's 3 times as big. So this is 2 to 1, this is 1 to 1, and this is 3 to 1. Okay, so again, I screwed up with the curve. I thought I was going to do a good job. So we'll have to use my pre-drawn curve. Okay, let's zoom in on this guy here. Okay, so this is exactly, let's zoom in a little more, just to this square. A little more. Are we at the limit? Okay, we've hit the limit. So this is that fundamental curve. It's a straight line. This is the second order. You can see the slope here is 1. The slope here is 2. I go factor of 10. Second harmonic increases by 100. And you can see that this term increases with a slope of 3 to 1. Now, this picture is very interesting. First of all, if I keep plotting the fundamental, eventually I get this deviation from linear. This is what we call gain compression. Why does this happen? Okay. Anybody want to take a guess? You want to use the mic?
Subtractive effect of the third harmonic.
Very good. Remember, we found that for very small signals, the fundamental is essentially generated by the linear term, A1. But remember, we looked at the cubic term, A3, and we found that A3 also produces fundamental. In fact, what we showed was any odd power will produce fundamental. And depending on the sign of A3, A5, A7, and so on and so forth, that might be subtractive. And so here, I'm assuming that it is subtractive, and so it's compressing the gain. So the gain's going down for large signal input. Okay? Same thing happens here. You can see the second order follows this 2 to 1 curve. That's when the second power is dominating the second harmonic. But when the fourth order term comes in, right, the slope should change to 4 to 1. The sixth order comes in, the slope should change to 6 to 1. So we see the slope going way up here. Likewise for the cubic term. So the region where we say this system is weakly nonlinear is to the left here. In other words, our analysis is valid as long as the second order distortion is dominated by the second power. The third harmonic is dominated by the third power, and so on. Okay? Any questions about that? That's a very important point which will come up later.
Does the curves necessarily go up, or?
Good point. Not necessarily, but physically, eventually we know that this curve, for instance, for the fundamental, should compress. Because remember, eventually the output has to saturate. Eventually the output can't grow beyond a certain amplitude. So in this case, let's say, this is a pretty wimpy amplifier if it compresses with, 1 millivolt. But let's say eventually at supply voltage it has to compress, right? It can't ever swing above supply unless there's really weird stuff going on in your circuit. Okay? Don't want to make a general statement, but for most circuits, you're going to compress eventually. Okay? Good questions. Any other questions or comments about this? Now, when you go home and you're looking at these slides, just convince yourself that the slope here is 1 to 1, the slope here is 2 to 1, and the slope here is 3 to 1. Good. All right, get rid of this bad picture. So we are on page 5. All right, so now let's talk about some distortion metrics. So the way we characterize an amplifier is by specifying the distortion through various ways. One common way of doing it is called fractional harmonic distortion. What we do, for instance, HD2 is the amplitude of the second harmonic normalized to the amplitude of the fundamental. Okay, so now if we assume that A2S input squared dominates the second harmonic, in other words, A2 cosine omega 1 t squared, which is equal to 1/2 A2 1 plus cosine 2 omega 1. If this dominates, then we can see that HD2 is simply 1/2 A2 amplitude of the signal. Let's say that the input is S1 cosine omega t, so S1 is just the amplitude. So I get S1 squared divided by the fundamental at the output, which is just A1 times S1. In other words, the second harmonic is 1/2 A2 over A1 times S1. Okay? Any questions about that?
Why should the second harmonic be of concern if it does not generate any in-band frequency
Okay.
component?
The second harmonic is of concern because, first of all, it's generating distortion in someone else's band, right? Might not be your band, but someone else exists at second harmonic. Secondly, because it generates DC. And that DC is actually going to compete with your signal. If you have a low IF or ZRIF system, then that DC is going to corrupt your signal. So it is, in fact, very important. But very good question. For those of you who didn't follow, we'll talk more about system-level issues probably today, actually. We'll get to there. Okay. Well, in a very similar fashion, I can define my third harmonic. Also, a second answer to your question is, this analysis not only applies to RF amplifiers, but also every kind of amplifier. So for instance, let's say you have a cable TV amplifier, a video amplifier. Well, there's very likely, if you're watching 100 megahertz, there's going to be another channel at 200 megahertz someone's watching. So again, second harmonic matters. You might be dealing with an ultra-wideband system where second harmonic falls in band. Or something as simple as an audio amplifier, right? If the musician intended you to hear 5 kilohertz and you're outputting 10 kilohertz, again, it's not a very nice thing to do. All right. So third harmonic, HD3, is again the amplitude of third normalized by the amplitude of the fundamental. Okay? And last lecture we found that the amplitude of the third, actually we just redid it at the beginning of the lecture, is A3 S1 squared divided by 4. And again, the amplitude of the fundamental for weakly nonlinear systems is just A1 S1. And so the HD3 is A3 over A1 S input squared 1/4. Yes, thank you. Good catch. All right. Now I can also rewrite these in terms of the output. So the output, S1 is the input. The output is A1 times S1. So I can write HD2 also in terms of the output signal. So in that case, I have A2 over A1, and I can just substitute SOM over A1. And so I get 1/2 A2 over A1 squared SOM. And if I substitute into HD3, I get 1/4 A3 over A1 cubed SOM squared. Okay? Questions or comments about HD2, HD3? Now, if you have an old-fashioned radio in your house or maybe an amplifier, go open up the cabinet and look at the technical specs. A lot of times they'll tell you the specifications for harmonic distortion. In fact, more than likely, if it's an audio system, they'll tell you the total harmonic distortion. So let's look at why the total harmonic distortion is significant. So let's start out with the signal power. So our output signal is basically a Fourier series. We put in a sinusoidal input, and output we have basically some signal at the same frequency plus all the harmonics. Now remember, a linear system cannot generate output frequencies that are not in the input frequency, a linear time invariant system. So you need a nonlinear system to make this happen. Okay. Now, by Parseval's theorem, we know that for a periodic signal, if we want to calculate its power, let's say over one cycle, we basically can take the sum of the magnitude squared. So I could sum, well, actually I guess I did this a little bit more messy than I'm just going to derive real quick Parseval's theorem. So if I take v squared, I'm just going to substitute what v is here. So this is VOK times cosine k omega 1t dt. And I use j and k so I can distinguish them from each other. And I can, since hopefully there are no mathematicians in the room, I can just change the order of summation and integration without upsetting anybody. And I get this result. And we know that as long as these integers are distinct, if they're different, then over one cycle, cosine is basically orthogonal to cosines of other frequencies. So this simplifies to sum over jk 1/2 delta jk, this is the Kronecker delta function, Voj, Vok, and of course that means the double sum breaks down into a single sum, 1/2 j Voj squared. Okay, so that is Parseval's theorem. Which tells you that the signal power is related to the power in the harmonics. Okay, and that's because we've done an orthogonal expansion on the signal. So applying Parseval's theorem tells me that the power in the distortion divided by the power in the fundamental is simply VO2 squared divided by VO1 squared plus VO3 squared divided by VO1 squared plus all the other harmonics. And of course, what do we call this? We call this ratio HD2, so it's HD2 squared plus HD3 squared plus HD4 squared, and so on. Okay? So we define the total harmonic distortion, or the THD, as the square root of HD2 squared plus HD3 squared, and so on. So next time you go to a fancy hi-fi audio place and they tell you the THD is 2% or 0.1% if it's a fancy place, ask the guy, what does it really mean? You know, see if he knows Parseval's theorem. All right, so let's give you some examples for telephone. If you make a phone conversation, even a landline, sounds pretty crappy, right? THD is could be as large as 10%. Let's say high quality audio. Anywhere from 1% to, if you pay a lot of money, if you're really stupid, as little fraction of a percent as you want. The reason I say if you're stupid is because really the speakers, and it's hard to find speakers that are better than 1%. So if you buy this super fancy amplifier that puts out 0.001%, the speaker is going to dominate anyway. Video. Turns out that even though our eyes are pretty sophisticated, they're pretty forgiving to distortion. So you would have no trouble watching video with 5% THD. Unfortunately, our webcast has about 50% THD. If you're looking at, let's say, analog repeaters, they need to be very good. You're not stupid for buying a repeater that has this little distortion, because if you think about sending video from, let's say, your cable operator down to millions of homes and having repeater amplifiers all along, we'll see that if the distortion levels aren't very well controlled, all the channels would get mixed up. We'll see that actually. So you'd be watching channel 5, but you'd see a ghost of channel 6. So it's very important to keep these levels down. In fact, in RF systems, similar things happen. So for RF amplifiers, we also need very good performance, again, on the order of 0.1% THD. Okay. Any questions about harmonic distortion? All right. So harmonic distortion.
Well,
yes. No, we're going to talk about that later. Yeah. Okay. Any other questions about harmonic distortion? Okay. So now we're going to talk about intermodulation distortion. Okay. So far we basically, all we did was we put one tone into a nonlinear system and found that it generated all these harmonics. Well, what happens if you put more than one tone? Let's say I put in 2 tones. This is a so-called 2-tone test. Now, same formula applies. I have a power series. And I'm going to look to see what each term does. Let's look at the second power. So the second power is going to basically generate S1 squared cosine omega 1 squared t plus S2 squared cosine squared omega 2t plus 2 times S1 S2 cosine omega 1t times cosine omega 2t. Now these first 2 terms we've already seen. This will generate DC plus 2 omega 1. That's the second harmonic. This will also generate DC plus 2 omega 2. The interesting term here is this term. This is a mixing product. And this is something new that we didn't see before when we just put in one tone. What we see is that I take the product of these two, and again, applying what we learned before, product of 2 cosines gives us the sum cosine and a difference cosine. So the output, the mixing product, we call this the second order intermodulation term. And I have 2 S1 S2 times 1/2. Actually, I don't. Yeah, these cancel out. So 1/2 cosine omega 1 minus omega 2t plus cosine omega 1 plus omega 2t. Okay. So this is totally new. We see that if I draw a picture, let's say this is DC. This is omega 1. Let's say this is omega 2. I put in two tones, let's say, at these frequencies, and I'll generate 2 omega 1 and 2 omega 2. These are the second harmonics. I generate DC. But then you can see that there's this difference frequency. I generate that here. This is omega 1 minus omega 2. And I also generate omega 1 plus omega 2. So these are the intermodulation distortion terms. Okay? Questions? So just like I defined an HD2, I can define an IM2. This is the amplitude of the intermod terms divided by the amplitude of the fundamental. And what I'm going to do is I'm going to make my input signal have two tones of equal amplitude. Okay? And if I just plug in these two tones, if I plug in to IM2, I can see that I generate S input squared times A2. So IM2 is simply A2 S input squared times A1 S input, which is just A2 over A1 times S input. And incidentally, this is the same formula that we derived for HD2 with a scaling factor. So IM2 is 2 times larger than HD2. In other words, it's HD2 plus 6 dB on a log scale. Okay? Questions or comments about this?
What's the difference between omega 1 and omega 2 usually?
Okay, so the question is, what's the difference between omega 1 and omega 2? It can be anything, right? This holds arbitrarily. So it could be two tones very close together, it could be two tones very far away from each other. Regardless, they'll generate intermodulation terms.
So can you assume that the FFR behaves about the same for both frequencies?
That's a very good question. Remember, this is a memoryless system. So the key assumption, so in answer to your question, is we assume a memoryless system. Now, by definition, a memoryless system means that there is no frequency response. It's flat. Now, you might say that's a really, really gross approximation, but what we're doing is we're separating our system into, let's say, filtering, and then nonlinearity, and then maybe filtering. So if we do have an LC tank at the input, at the output, we would actually apply it before and afterwards. Okay, that's a great observation. Anything else? Anyone else? All right, so what are some of the practical effects of IM2? So let's say we have a communication system that uses the bandwidth from 800 megahertz to 2.4 gigahertz. Okay? And let's say we have two unwanted interferers at 800 megahertz and 900 megahertz. Okay? Then we know that when these two things interact with the second order nonlinearity, we generate distortion at 100 megahertz and 1.7 gigahertz. And both of these, so this term, the higher order intermodulation, happens to fall in band. So if there were another channel at 1.7 gigahertz, it would have to compete with this distortion term. Okay? Now you might say, well, these distortion terms are always really small, right? That's the whole assumption for weak nonlinear analysis. So what's the problem? Well, the problem is that if you think all the way back to lecture 1, we talked about the fundamental issue with wireless communication is the dynamic range of signals varies greatly. So sometimes your signal is strong, sometimes it's weak. So let's say you're in a situation where we draw a band where your signal at 1.7 gigahertz, is say here, is very weak. And let's say that the people transmitting on 800 and 900 megahertz have very strong signals, right? Much bigger than your signal. So they're going to generate distortion that's going to fall in band. And even though that distortion is small compared to their magnitude, it can be large compared to your magnitude. So this could completely swamp out your signal. So our signal is swamped by distortion, potentially. Okay? So in a wideband system, in answer to the earlier question, certainly we need to worry about second harmonic, third harmonic, and intermodulation. What about a narrowband system? One solution would be, okay, if you have a narrowband system, then both the difference frequency and the sum frequency are always going to be out of band. But it turns out that there are certain situations, like a low IF receiver, where we're using either low IF or direct conversion, where the IF frequency or the intermediate frequency is low frequency. Remember, in a communication system, what we do is we take our RF signal, let's say off the antenna or off the cable, we filter it, we amplify it, and then we mix it down using a local oscillator to some IF frequency or intermediate frequency, where we perform filtering on it, very sharp filtering. And then we digitize the signal. Okay? So in this system, even though we have a very narrowband input, our IF could be really low frequency. So let's say our IF is DC. Let's say we have a direct conversion receiver. In that case, because IM2 generates omega 1 minus omega 2, if I have two channels that are really close together, so let's say these are two channels, omega 1, omega 2, and let's say this is the desired channel. And let's say that this is my IF. So my system tries to convert the desired channel to the IF, but because my system has some second order distortion, maybe in this LNA, maybe in this mixer, it will generate distortion that will compete with my signal and possibly make it impossible to communicate. All right? So even narrowband systems are not immune to second order distortion. Any questions about that? It used to be that people didn't worry too much about IM2 in communication systems because communication systems used a relatively high IF frequency. And so you basically could AC couple and get rid of the DC offset and that wouldn't be an issue. Nowadays, it turns out that these kinds of architectures with low IF are much simpler to integrate. So either direct conversion or low IF, and they require minimal filtering. So for these systems, which are increasingly popular today, especially for things like CDMA, wideband CDMA, this IM2 problem is a very serious problem. Okay. Now remember last lecture, what did we say about odd order functions? Kevin?
On polynomials,
Yeah. What was the nice thing about odd order functions?
they don't generate
They don't generate
DC.
any even order distortion terms, right? So if there's no even order distortion, we wouldn't generate any intermodulation. So in an ideal world, if we made all these signals differential, we wouldn't have to worry about IM2. Is that true? Why not?
Because if we have another one and another two rays very close to each other, and we have the third harmony, then
Okay, you're getting too complicated.
yeah.
Forget about third harmonic. So let's just say, for this system, would that be an issue? If I had differential architecture, would that solve the problem? No? Yes? Well, remember, you can never build a perfectly differential signal path. There's always going to be mismatch. So there will always be residual second order due to matching constraints. You know, in integrated circuits, you build two transistors, you make them the same size, they come out different, right? Because they're so small, there's going to be lots of variation due to doping, due to lithography, and so on. Okay. Well, what's also very important, traditionally very important, still important, is cubic intermodulation, or third order intermodulation. So again, if we do that two-tone test, if we put in two tones and we look at the third power, we have S1 cosine omega 1t plus S2 cosine omega 2t, and we cube it. You can see that when we do the expansion, we're going to get cubic of this term and cubic of this term, right? Those terms we've already dealt with. That will give us fundamental and third harmonic. So we'll get 3 omega 1 and we'll get 3 omega 2. So we'll generate 3 omega 1, omega 1, 3 omega 2, omega 2, right? What about the cross terms? Well, one cross term is this squared times this. So we get S1 squared cosine omega 1t squared times S2 cosine omega 2t. And the coefficient is 3. So if I now multiply this out, so let me call this a cross term. I'm going to get 3s1 squared s2, 1 plus cosine 2 omega 1t, 1/2 cosine omega 2t. And if I multiply this out again, I get 3/2 s1 squared s2 cosine omega 2t plus 1/2 cosine some frequency 2 omega 1 plus omega 2t plus cosine 2 omega 1 minus omega 2t. Okay? Now this is again something we've seen before. This is just more generation of second harmonic. These two terms are the intermodulation terms that we're looking for. We can see that we generate a tone that's 2 omega 1 plus omega 2, it's a new frequency, and 2 omega 1 minus omega 2. So these are the very important intermodulation terms. Just say, yes, that's what we're looking for. So we can see that the third order intermodulation terms we did this for one cross product, right? I took this squared, this linear. I could do the other way around, and you'd say I get two more. I don't have to redo the math. I can just interchange 1s and 2s in that equation. So the intermodulation terms look like 3/4 cosine 2 omega 2 plus or minus omega 1. Okay? And so by symmetry, I can just rearrange coefficients. We also generate, so this one has A3 S1 S2 squared. This one will be A3 S1 squared S2 3/4 cosine 2 omega 1 plus or minus omega 2. Okay. Now, what's really interesting about these terms is, if you notice, let's say omega 1 is approximately equal to omega 2. Two tones close together. What happens? Well, then 2 omega 1 minus omega 2 is approximately omega 1. So this IM3 falls right on top of input signal. In other words, before we had to dream up these weird scenarios where there were these two signals and they were just spaced right and they intermodulated and then they produced distortion, right? That hurt us. Here, we don't have to be very creative, right? The signal is going to interfere with itself. You might say, well, that still requires two tones, but really any modulated signal has infinite number of tones in it. So if I have a modulated waveform and it goes through nonlinearity, the third order intermodulation distortion is going to produce frequency right in band. So I'm going to create a signal that competes with itself. Let me draw a picture. So the idea is I have frequencies omega 1, omega 2, and I go through a third order nonlinearity. I generate 2 omega 1, omega 2, and 2 omega 2, omega 1. So this is 2 omega 2 minus omega 1. This is 2 omega 1 minus omega 2. And the spacing here is always the same. It's omega 1 minus omega 2. I didn't do a very good job to show that. But the idea is that these frequencies now can be very close to the band. Like this might be the band that you're interested in. And these two tones could represent two modulation components, right? I mean, let's think of a very idealized scenario. Let's say these two tones correspond to two people singing a pure tone, right? Two opera singers producing two tones. The harmonics are out of band, but now this nonlinearity produces two more tones. So we have these two baby opera singers who weren't supposed to be there. And they fall in band. That's the key point. All the other distortion, we could imagine a scenario where we filter them out. So for instance, I know that I'm also going to produce omega 2 minus omega 1, right? And I'm also going to produce omega 1 plus omega 2 due to second harmonic. But look, I could put a filter here and get rid of these terms. I can't filter out these terms because they're in band. Okay, question?
Yeah, but here we don't have the problem that the signals causing the intermodulation are much stronger or can be much stronger than the signal itself.
That's a good point. That's a very good point. Now there's two scenarios where this still does matter. One is in power amplifiers, because they produce large signals. So power amplifier will self-interfere. In other words, you put in one spectrum and out comes another spectrum that has components that weren't in the original spectrum. And then the other scenario is you still have basically neighboring channels. In most communication systems, you break up your band into, even a narrowband communication system, you'd break up your spectrum into multiple channels, right? Let's say you had a megahertz and you broke it up into 10 100 kilohertz channels. Okay, so let's do a very simple example. Let's say this is 1 gigahertz and this is 1 gigahertz plus 1 megahertz. So an extremely narrowband system. and I divide this into, let's say, 10 channels, each 100 kilohertz. Now 100 kilohertz is a good enough bandwidth to carry voice, even FM modulated voice. So that seems very reasonable, except you say this is very narrow band, so if I have 2 channels here, 2 people talking, second order distortion is going to fall way out of band, right? But their IM distortion is going to fall into channel 0 and into channel 3. And if you happen to be on channel 03, you're going to get hit. Okay? Good question. Okay, so we see that IM3 is very important. So let's define it. IM3 is defined just in the same way that we defined IM2. It's the amplitude of the third divided by the amplitude of the fundamental. And we do all the math, and it's simply 3/4 A3 over A1 S input squared. And if you look back at the expression for HD3, you can see that IM3 is 3 times larger than HD3, or approximately 10 dB larger than HD3. All right, any questions? Comments? Okay, so let's look at the complete two-tone response. So here is a picture that we zoom in on. Can we get max zoom? Someone knock on the window. Can we get the max zoom on this picture? Thank you. All right, so it's a little grainy. But you can see these are the 2 tones we put in. And then you can see that I'm going to get second harmonic, I'm going to get third harmonic. Then I get second order intermodulation here and here. I get third order intermodulation right next door. I get fifth intermodulation right next door. I get seventh intermodulation right next door. And what you find is, if you do the detailed analysis, is that if you have an nth order power, then you get frequency components j omega 1 plus or minus k omega 2, where j plus k add up to n. So for instance, for second order, you can see this equation tells you that you get omega 1 plus omega 2 and omega 1 minus omega 2. For n equals 3, a third order distortion, you get basically 2 plus 1 is equal to 3, 1 plus 2 is equal to 3. So I get 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Right? And plus or minus. So in general, all odd order powers generate distortion products which basically go right next door to your fundamental signal. So if you're worried about in-band distortion, you really worry about odd order distortion. In particular, the strongest term is your IM3 term. And then next you have your IM7 term, and so on. IM5, and then you have your IM7, and so on and so forth. Okay? So it's interesting. If I encourage you guys to go and look on the spectrum analyzer. Take a nice innocent looking amplifier, put 2 tones in it, and look at the output spectrum, and you'll see something like this. And no matter how small you make the signals, there always will be this distortion present. It's just usually so small that it's below the noise floor. You don't notice it. But if you turn them up, if you turn up the signals, eventually they'll creep up above the noise floor and they'll start hurting you. Okay? Questions? All right. Well, there's a few other kinds of distortion that we'll talk about. In particular, let's talk about distortion of AM signals. Now you might be thinking I'm crazy, right? Nobody uses AM anymore, right? When's the last time you listened to an AM station? Pretty much AM tells you your age. Okay, you must be 70 years old. You always see these old guys carrying their little transistor radios, listening to the game or the news or the weather. But actually, amplitude modulation is used a lot in digital form, in particular. It's also used for video. The video you're watching, it's very inefficient, but it's amplitude modulation. The reason it's amplitude modulation is that amplitude modulation is more spectrally efficient than phase modulation or frequency modulation. So even though on televisions we'd like to use FM, but that would use up too much spectrum. So we use AM for the video and we use FM for the audio. So the audio is actually sent through FM, but the video is amplitude modulation. Now, with amplitude modulation, we can represent the signal in this generic form. And because the mathematics gets way too ugly, we're going to assume we have a carrier, that's omega 2, and it's being amplitude modulated by one tone, omega m. In general, I should write m of t as the modulating waveform, but here I assume that I just have one tone of modulation. So m, which is less than or equal to 1, is the modulation index. And so I can expand this product out using cosine 1 times cosine 2, which is sum and difference cosines, and I get basically three terms: m over 2 cosine omega 2 minus omega mt plus m over 2 cosine omega 2 plus omega mt. So this is the carrier. This is the lower sideband, and this is the upper sideband. So we see that this modulation waveform produces two sidebands around the carrier, and usually we would, depending, lots of variations on how the signal is sent. Sometimes the carrier is suppressed. That's called carrier suppressed amplitude modulation. In this course, we're not going to worry too much about the communication circuit details. What we'd like to look at, though, is what happens if I put this AM system through some kind of nonlinear distortion, some nonlinear system. Okay, so what I'm going to look for is called cross modulation. And the idea of cross modulation is maybe somehow, of course this was observed experimentally, but what happens is, I can just describe it experimentally, you have two channels. They're both amplitude modulated. You go through a nonlinearity, and then all of a sudden one channel contains a copy of the modulation from the other channel. So even if there were no modulation on another channel, all of a sudden the video, let's say, gets transferred to the other channel. Well, that's really annoying. You're watching your soccer game, and all of a sudden you see someone dancing in front of you. Even if it's faint, you only want to see soccer players dancing. So what we're going to see is, let's say we have this wanted signal, and we assume it's blank, but somehow or another we're going to see a modulation, cosine omega 1, appear at the second frequency. So this is our wanted signal. This is our interferer. And the cross modulation term will look like this. In other words, this unmodulated waveform at omega 1 gets modulated through the nonlinearity and appears as a modulated waveform cosine omega 1t. Okay? So we haven't shown how this happens. We're going to do that now. So what we do is we take the output signal as A1 linear term. We know the linear term obviously won't produce cross modulation. Second power, third power, and so on. And we do all the ugly math, and we find that the second term does not produce cross modulation. No matter what term you look at, you never get a transfer of modulation from one waveform to another. So we look for the third. Okay. Let me try to keep this here. So let's expand the term A3 S input cubed. And in particular, if you look at the term, so here's our unmodulated waveform, and it gets multiplied due to the cubic by the modulated waveform squared. Sorry about the ugliness here. So this is the modulated waveform squared being multiplied by the unmodulated waveform. So if we expand this, we get 3a3 s1 s2 squared cosine omega 1t times this term squared, which is simply 1 plus 2m cosine omega mt plus m squared cosine squared omega mt, all times this term squared, which is 1/2 1 plus cosine 2 omega 2t. Okay? And so now we're going to group the relevant terms, and we'll see a1 s1 1 plus 3 a3 over a1 s2 squared cosine omega mt times cosine omega 1t. Okay, so looking out here, we can see that I have this fundamental being multiplied by 1 plus this modulation term. So I'm going to multiply this out by this, and you can see that what I'm looking for here is in the product, when I multiply everything out, I should just have a term at cosine omega t. So this term times this term does the trick, right? And when I expand out this term, I'll get one term that gives me another term. So that's where the 3 comes from. So again, the math is ugly. I'm kind of hand-waving it away. But the interesting thing is that we see cross-modulation happening much more clearly in the notes if you spend some time. So we have the transferred modulation index divided by the incoming modulation index. And so that means that cross-modulation is proportional to A3 over A1 S2 squared. It's just this term here, which turns out to be 4 times larger than IM3. Or it's in dB, IM3 plus 12 dB. Okay? Now this sounds very complicated, but a picture is worth 1,000 words here. So let's look at the picture. This is a simple picture. I have an unmodulated waveform coming in. It goes into a nonlinear system. Some other signal is being modulated, and yet at the output, at frequency omega 1, I see amplitude modulation. So this is why we call it the transfer or the cross modulation, because this signal was not supposed to be modulated. Again, this is the channel showing the soccer, and these wiggles are somebody dancing on the screen. So that's what we don't want to happen. Okay? Any questions about cross modulation? Now we've looked at the impact of distortion on your system. Second harmonic, third harmonic, second order intermodulation, third order intermodulation, cross modulation. In some ways, this is just the tip of the iceberg. These are the important modulation terms if you're dealing with narrowband communication systems. If you're dealing with a digital communication system, things get even uglier. But you might think this is ugly enough, so let's not go too much further here. Okay, so now let's do an example. You know, we've done lots of math, and maybe you're lost. So it's always good to come back to something practical. Let's look at a BJT amplifier. Bipolar transistor. Simplest transistor in the book, right? Common emitter amplifier loaded by a resistor. Okay? Now I'm not showing the biasing just to make it simple. So the output VO is simply VCC minus IC times RL. Okay? And IC is equal to IS e to the q VBE over KT. And VBE here is equal to Vs. So I can write IC as two terms, e to the q VBEQ, the quiescent bias point, times e to the q V input over KT. In other words, I assume that the input VBE is some DC value, which is the quiescent operating point, plus some small signal. Okay? Now, if we were doing small signal analysis, essentially we just take the linear term when we do this approximation, when we do this expansion. Now we're going to do the full expansion. We know that an exponential function has a very nice Taylor series expansion, which has a very large radius of convergence. Looks like that. And because we basically don't want to make things too messy, we'll keep things up to the third order term. So now let's substitute this expansion for this term here. So essentially I can write that IC is equal to ICQ e to the q V input over KT. So ICQ is just the constant bias current. And then I do a Taylor series expansion for this exponential. I get DC term plus a linear term, which is V input normalized to VT, which is KT over Q, plus 1/2 V input over KT squared, KT over Q squared, plus 1/6 V input over VT cubed, and so on. Okay? So now the signal current is the output current minus the bias current. So the signal output simply looks like ICQ over VT times the input plus this term, 1/2 Q over KT squared ICQ V input squared plus, I'm just expanding these terms, 1/6 Q over KT cubed ICQ V input cubed, and so on. All right? So what is this term? Look familiar? GM, that's right. So we see that A1, so I want to write output is equal to A1 times input plus A2 times input squared plus A3 S input cubed. And so I just now identify each coefficient. A1 is Q over ICQ over KT is simply the GM of the transistor. So now we see a nice unification between large signal analysis and small signal analysis. We did small signal analysis, we just ignored all these other terms, and so we had this nice simple result that the output current is just GM times the input current. Now things are a little more messy. But it's not too bad, it's just a power series. So A2, which we found is 1/2 Q over KT squared times ICQ, and we found that A3 is 1/6 Q over KT cubed ICQ. Okay. Any questions? Well, this is a pretty powerful result. What we've shown is that for any BJT in common emitter configuration, and this could be a silicon BJT, it could be a silicon germanium BJT, it could be a germanium BJT, gallium arsenide BJT, because all BJTs have this exponential characteristic, universal characteristic, and for all of these circuits we found that HD2 that's generated is 1/4 Q times the input amplitude normalized to KT over Q. Okay, so V input is the peak input amplitude. All right. So let's say that the input amplitude is 10 millivolts. Okay. If I plug in 10 millivolts, KT over Q is roughly 25 millivolts, and take 1/4 of that, I get that HD2 is 0.1, or about 10%. Okay. That's actually pretty shocking, right? Because 10 millivolts is a pretty small voltage. So I put in 10 millivolts into this amplifier, and output has 10% second order distortion. Right? You could hear that. We could also express HD2 in terms of the output current. Remember, we found that HD2 is 1/2 A2 over A1 squared times the magnitude of the output. So plugging in, that gives us 1/4 the collector current amplitude divided by ICQ. So for instance, for IC over IQ, let's say of 0.4, we also get 10%. Now this gives us a formula for how to reduce the distortion in the amplifier. What do? I have to run more current through it, right? I have to increase the bias current. And the more bias current I run, of course, the more power I dissipate. So to create a very linear amplifier means that I have to run lots of current through it, and I can't swing the output current too far beyond the bias, the quiescent point. Okay. What about IM3, which is more relevant for communications? Let's say I want to build a communication receiver, and I know I can't handle more than 1% IM3. Well, let's solve for IM3 of 1%. So IM3, which is 3/4 A3 over A1 times S input squared, gives us 1/8 QVI over KT squared. And if I solve that, I get that the input can't be larger than about 7 millivolts. Again, that's a pretty small voltage. 7 millivolts. Usually we like to send healthy signals which are much above the noise floor. And in some systems it may turn out that 7 millivolts is too small. Let's say I'm going to send a signal for 10 miles, and I know it's going to get attenuated by 60 dB. Well, I want to drive it so it's large enough so that by the time it gets to the receiver, it's still, let's say, hundreds of microvolts or tens of microvolts. So certainly I'm going to need to amplify a signal bigger than 7 millivolts. So this common emitter amplifier, very simple, has a serious problem with distortion. It's very, very nonlinear. Okay. So next lecture we'll look at ways of improving the linearity of these amplifiers. Don't forget that your homework is due today.